Hello, everybody.
Hello.
Okay, so we postponed the homework. Let me zoom this in. At the last moment in the last class, we postponed the homework to February 24th. That's Wednesday. And next thing is we have a midterm in between. Like I think expect the next homework to be due on Wednesday, 1 week from then, but I'll decide that tonight. That's a couple of announcements, and I haven't decided on the date for the next homework yet. And the homework solution for this current homework should be out sometime today. Later in the day, but surely today. Okay, so let's proceed, and I suggested that we go over whatever I did in the end of last class more slowly today. So let me attempt on that. I should also say that we do see this part again in a lot more detail in the later part of the semester, somewhere in chapter 9. So this is sort of a, let's say, a trailer for what's coming in the future when we really talk about rotational motion in complete generality. But let me try to give a summary of that anyway. So let's go back and remind ourselves of, yes.
Discussing quiz 219 as well.
Tell that again.
Are we discussing quiz 219 as well?
Oh, yes. Oh, this time I had thought that I will do that without you guys prompting me. Okay. Sorry about that. Yeah, this was about gravitron. I did. So this is, yeah, quiz 0219. Right? This was about gravitron. Again, this was really an open-ended question in the sense that you don't have all the information to answer the question right away. Some of the concepts will come in probably 2 weeks down the line. So here is an extreme version of this. Think of a cylinder. I hope you guys have seen some of the videos in there. So this is a cylinder. And it is rotating about an axis like this. So this whole cylinder is rotating, and you're standing by here. Again, presuming that you have seen some of the videos, this is a simplistic version of this, just one cylinder rotating, and you're standing here, and the expectation is that there is a floor down there on which you can stand. Let me replace this person with a mass m itself. So if you have a mass m, the simplistic version of that. And you always expect that if a mass has to be standing, it needs a floor, correct? But the idea is that if there is something moving around, we have a centripetal acceleration. Notice something is rotating. So rotation, whenever there is rotation or circular motion, there is an acceleration, inward acceleration. So radially inward acceleration. And we haven't completely grasped this, but the idea is that acceleration, there is a one-to-one correspondence between acceleration and gravity. G, like that we experience, actually it is the acceleration that we are experiencing. And in principle, whenever something is accelerating, if not for our body having some other reference, we might sometimes confuse it with the gravity. We might think that there is a stronger acceleration and so on. I should put it downward. So, so the point is acceleration and gravity, that could be a one-to-one correspondence. Again, this is a futuristic thing in the sense 2 weeks down the line, we will have more concrete information. But we do know that there is a radially inward acceleration. So that's your centripetal acceleration down here. So that's centripetal acceleration. Why is there an acceleration? Because it's going rotating. And if we were standing inside here, we can get confused with gravity being associated with acceleration in what direction, but I'll keep it still open because there is another quiz coming that is due on Wednesday. I will ask you, what is the direction of gravity if there is a centripetal acceleration inward? What is the direction of the perceived gravity? So why does this go around? As far as there is an acceleration here, this is the acceleration, and we will see that for every acceleration, there has to be a force. This is going to come in pretty much on Wednesday, but the idea is that if there is an acceleration, there is a force. So since there is a wall here that is going to be pushing on you, and that is why it actually tries to move outward. We will get to the details in there. Does that help a little? I would like you to ask questions because I have not thoroughly answered it because we haven't studied it completely. Any questions or concerns there? There should be. Okay, so if not, I will leave it with the idea that think more on this acceleration and gravity. They are very related to each other. We perceive acceleration as if there is gravity. Okay, so that's an idea of a gravity. We will get to clarify this perfectly within a week or so. That's sort of a warm up. Okay. If no questions, I will proceed. Let's see, one. Okay, I want to do something on, yeah, we were doing circular motion. So let me remind ourselves of vectors first. Remember, vectors is pretty much having the idea that there is a magnitude and a direction. That's your vector. Earlier, we have said a general vector to be A. Let me this time call it the vector R. So let's say this is R. Write that here. So that's vector, position vector R. We have said that this is your Y, that's your X, and we specifically said that this is I hat. This was the direction, this is the direction of X if you want. You can also, I also said that sometimes we will call it X hat. So X hat is also good. That's your j hat. Specifically, we have the position r to be equal to x times I hat plus y times j hat. And we have used vectors sufficiently now that we know that these two coordinates specify this vector completely. But we also said that is an intuitive field for a vector given in terms of the angle. This could be theta or phi. Sometimes we use phi. In this lecture, I will use phi. Earlier, I have used angle theta in here. Same thing. And the magnitude of this vector, I'll call it r. And r and theta or r and phi are your polar coordinates, right? So we notice that x comma y, we need two information for the vector, either the components. So these are the components. You can say rectangular components, or we said that is r and theta, magnitude and direction, right? And if you've seen polar coordinates, this is very similar to polar coordinates. Like actually one-to-one connection between polar coordinates and angle theta, angle and direction. So this is again the magnitude of the vector. This is the direction of the vector. Oops, phi, right? I didn't mean to say theta. Okay, so let me go back and look at this polar coordinate, vector r again. And this is equal to x is connected with the polar coordinates by r times cosine phi in the I direction plus r times sine phi in the j hat direction. That shouldn't be very new. That should be exactly the same. But now I want to separate out as much as possible the direction or the magnitude, one of the quantities out of this. If I want to separate x and y, it is the I and j that separates it, but I want to separate out the magnitude from the direction of the vector. Remember, a vector has a direction and magnitude to it. So I notice that there is an r in here. So I define what is called vector r divided by its magnitude r. So this is the magnitude. Remember, magnitude of the vector r is nothing but written simply as r. So that's quantity is nothing but magnitude of r. And that's, we notice that there is no more any information about the magnitude in there. It's all angle dependent. In fact, with this, we will call it the r hat. What does that mean? This is the direction of the vector r. Its magnitude has been pulled out. That means to say that it has been divided out. What do we mean by a little more on that? What is the magnitude of the vector r? What is the magnitude of the vector r? That will come out to be cosine square phi plus sine square phi, which we know will always be equal to 1. So even though we did this for a very special vector, in general, for any vector, I can define its direction by its vector divided by its magnitude. That's the idea of a unit vector or the direction of a vector. If we go back now, yes.
So the magnitude of the direction of the vector equals 1?
Yes, that's correct.
Thank you.
Okay, so for example, if you want a visualization of this, so this is a general vector. Let's say A, right? Think of a direction means this. This is your same vector, but with unit direction. So I can say A is 5 times this direction. If you're already in that direction, it is only scaled with its direction. So direction means it has that arrow in it, but the scale may not be exactly correct. Okay, hopefully that helps. So exactly what I said here, I can go back and actually write my vector as r times its direction. So this is the magnitude times its direction. Notice what I'm saying here. So this is the total vector. That's your magnitude. And that's its direction. So hat always represents the direction of the vector, and the magnitude is pulled out, right? So in that sense, r hat is cosine phi, sine phi. If I multiply by r, I get the total vector. So a vector can be split into its magnitude and its direction. That's the idea of the r hat. Any questions at this stage?
Yeah, I have a question. I'm confused. The last r for magnitude that you just drew, since it doesn't have the absolute value signs, like I'm confused when.
Okay, here at this stage, I think somewhere here, right? I used, can you guys see this?
Oh, I see.
And I'm defining this to be my r.
Okay, so that's just like the shortened version.
Just to avoid clutter. That's otherwise there are too many straight lines. That's all.
Okay, very good. Thank you.
So from this point on, a vector will have its magnitude when I'm not writing the arrow. That's magnitude, and when I write the hat, that's its direction. Okay, so that's the notation. A vector r without its arrow is its magnitude. Instead of an arrow, I replace it with a hat. That's its direction. So that's the notation. Okay. If I can proceed, let's see. Let's go back and see the vector. Okay. So again, draw the vector, right? Because idea is that I'm trying to work out a circular motion description. So that's going to be my vector. So that's one possibility. And let us say I also have, this is a circular motion, and that's an arbitrary non-circular motion, right? So this is circular motion. That's non-circular motion. In 2 dimensions, if it is not circular, a generalization of that is any arbitrary motion will be the generalization of a circular, non-circular motion. We're restricting ourselves to 2 dimensions at this point. Let's say this is our origin here. That's in general R. So that's R. And what do I mean by R? This is the position of an object that is moving in time. That's what I mean by motion, right? Something is moving in here, and this is a point object that is moving around at time t. So what is actually evolving, that's time t. At time t, this object is in here. At time t, this object is in here. So that's your position vector. The only difference now is that it has a time dependence. The position of the object has a time dependence. Like we had a projectile, it was evolving in time. If we go with our vector idea now, that's your vector position of this object, either moving in a circular motion or non-circular motion. Its time dependence is given in terms of 2 quantities. Now, its magnitude r, that's your magnitude of the vector, and a direction of the vector. But since this is going to evolve in time, both the magnitude and the direction can evolve in time. Right? Now, what is circular motion? We put a condition now. We say that this does not change in time. So circular motion, or here, let's say, r of t. Notice it's r of t, not the vector, it's the magnitude of the vector. R is a constant. That means to say that the length of this vector does not change. Right? Wherever you're on the circle, that's a definition of a circle, right? It doesn't change, but its direction is changing. But its length doesn't change. So this has to be a constant. That's not the case here. Right? The length of this vector is changing. This is r at time t prime. Another time t prime, its length has changed. Here, everywhere on the circle, its length remains the same. And let me further say this is capital R, just to signify that this is really constant. I will put it as a capital R. That was I think, a concern raised last time, but it's just a notation. Even if I say small r, that's very common. You would just write it as small r. But since we pointed that out last two lectures before, so I'm going to put that for r. So that means what has happened now is, now this is circular motion because its magnitude does not change in time, only the direction changes with time. So that's a special motion. So this is now circular motion. Or if we're going to make it more specific, its position is r cosine phi, but now its angle can change in time. So there is a time dependence in here, right? That's phi hat plus r sine phi of t times j hat. In general, this vector r could depend on time, but circular motion, this remains fixed. It's only the direction that is changing with time. Okay, that's good. So now we know about position. What about velocity? Right? Velocity, there will be two ways of going now, right? Either we can start from here or there. Now we go to velocity, we have to take the derivative of this. Right? In circular motion, what is the velocity of the point that is moving around? So velocity is derivative of the position with respect to time. If it was non-circular motion, there would be a time dependence in here. So it's more general, but this is significantly simpler in the sense we are doing circular motion, no time dependence here. It's only the time dependence in the vector, and the time dependence in the vector goes in the angle, like how the angle is evolving in time. So if I have to draw the diagram again here, just for reference, because it is there right above. So that's your position with reference to, that's your angle phi that is changing in time. And that's your vector r that's changing in time too. Its direction is changing, length remains the same, but this angle also changes as a function of time. As time evolves, this keeps increasing. So, so if I'm taking the derivative, it's the derivative operates on this function, which is the angle, and nowhere else because the length of the vector remains the same. But this is an arbitrary function. I don't know what it is, so you have to use chain rule. So when I take the derivative, this is r sine phi of t times d phi by dt. That's your first quantity. Notice I have used chain rule. First, took the derivative of cosine, which gave me a sine, and then the derivative of the phi itself, plus r cosine of phi of t times d phi by dt. Again, notice all these are common, exactly like the position vector. We observe something, and that is that if I were to take this common out, this is a time-dependent quantity, times minus sine of phi of t plus cosine phi, oops, I have j hat. Very similar to the earlier vector, and notice again this is a unit vector. So what is so if I were to redo this, let me do what is v hat, right? It's usually not said to be v hat, but let's do. What's the direction of velocity? That's what we are asking. When we take the vector itself and divide it out by the magnitude, and we ask what is that equal to, and that will involve dividing this out. You can take the magnitude and do this. This will be equal to minus sine phi of t times I hat plus cosine phi of t times j hat. Again, what's the length of this unit vector? It will be sine squared phi plus cosine squared phi. It will come out to be 1. Like always, when you divide out by its magnitude, its length will be equal to 1. We can call this v hat. Nothing wrong in that. By the notation we use, this should be v hat. Right? Perfectly fine by that notation, but we would like to call that phi hat. So this will be phi hat. Okay. Remember, your direction of the vector was or direction of a vector was phi in terms of r and phi, right? So this is in the direction of increasing phi, if you want, in the polar coordinate sense. So that's why you use phi hat. But this is nothing but v hat in the sense the direction of velocity. That's the direction of velocity. Any questions at this stage as far as algebra goes? I'll describe a few more diagrams with this in a minute.
Yeah, one quick question.
Yes.
So in the previous lecture, you had mentioned that dr over dt equals angular frequency times phi hat. That's the same?
That still holds. That's the next step. I'm going to do that in a minute. Okay.
Gotcha.
Yeah, that will still hold. Yeah. Currently, one step before that. Okay. Good. So.
Hey, Professor.
Yes, please.
So do we need to are we gonna have to memorize?
No. Nothing of this has to be memorized. First of all, this is all open book, open resource, right? Remember that. But if you want, how can I motivate? Okay, there are always two ways to prove something. Centripetal acceleration is an important concept, and I have shown you geometrically what happens. What is its direction? What is its magnitude? Here I'm doing algebraically, and more than that, I'm going to show you what if it is not a uniform circular motion. We are going to have an effect from the non-uniform part of it. Okay, that's what I'm trying to come to. So yes, like any other proof, I won't test you on the proofs, but there is understanding in there. So in that sense, it's very important. I can pick one small point in here and construct a problem, which will be important. So yeah, yes and no. If you're, since this is also intended for engineers, if it is a standard bridge you're repeating to construct, then you don't need to know this. But if you're building a new construction, then probably you need to understand it. That's a very weird way of saying it. Forget that. Yeah. Okay. Hopefully I answered that question. Okay. So let me draw a diagram again. So where do these things stand in a circle? That's your circle. That's your position, as I said, right? Position of an object that is going around the circle. That's your time dependence in here. And that's your angle phi. It's clear that this right triangle will give you cosine of phi, right? If this is unit length, this is your cosine phi, that's your sine phi, correct? That's clear. But now your phi hat, so our hat is cosine phi as a function of time in the I direction plus sine of phi in the j direction, correct? But I said phi hat is minus sine phi in the I hat direction plus cosine of phi in the j hat direction. time dependencies at each time, I can do this, but for visualization purpose, fix your time. So that's your fixed R. And what is your phi? This is in the, if phi is positive, let's say, this is in the second, negative says that this is either in the second or third quadrant. And this, if it is phi is less than 90 degrees, then I know that this will be in the second quadrant. So that seems to suggest that if you were to draw this, this will be somewhere here. Of the same length, if this is unit length, that's also unit length. That's your phi hat. Okay. That's your angle phi. But we also said that this is a direction of velocity. How is this direction of velocity? Move this parallelly. So that's your direction of velocity. Like we do know that when something is going in a circle or anything is going in a trajectory, the tangent vector gives you the velocity. That's your direction of velocity. Notice that it's tangent to that vector. So now if I go back, so there was a question just now that velocity was equal to R times d phi by dt, right, times there was a phi hat. Okay, that's your velocity. And again, direction is phi hat. But what is d phi by dt? That's a change in angle phi as a function of time. If you're going uniformly, now comes the uniform part of this. If you're going uniformly, not necessarily always uniform, like if you're going uniformly, that means you will go one circumference, that's 2 pi r, in a certain amount of time, that's a time period. Right? That will be equal to, we defined this to be omega times r, where omega was the angular frequency associated with the time period. So in that sense, this is equal to r times omega times phi hat. That's your velocity in circular motion or uniform circular motion. That's your magnitude of your velocity, length of your velocity. That's your direction of your velocity, right? Any vector can be thought of as a magnitude and direction. So that's the important piece I'm conveying. If you don't want the derivation, this is all I'm trying to grasp. Velocity has a magnitude, which is omega times r, times its direction, which is phi of t. But we are interested in acceleration. We want to go one more step. We want to take one more derivative of this. So for that purpose, let me bring in the time derivative again. Where is all the time derivative in here, or time dependence in here? That velocity as a function of time. So I'm rewriting the same expression, but I'm trying to emphasize where the time dependence is. In general, R could depend on time, but we are talking about circular motion, so that does not depend on time. In general, omega, which is how much angle is being going, how fast is it going around in the circle, that could be uniform or it could change with time. Right? This could go slower, faster, That's non-uniform. But if it is uniform, then that's a constant, and that's circular motion. So in general, let me put a time dependence in there. Okay. In general, this can be having time dependence, and phi hat, of course, depends on the time. Its direction keeps changing with time. So now I'm going to define two quantities. One is uniform circular motion. So the uniform circular motion means that omega as a function of time is a constant. Earlier we said the radius does not change with time. Now we are saying how much angle it covers in time t does not change with time. That's uniform circular motion. What is non-uniform circular motion? In that context, non-uniform circular motion, let's say, like that circular motion is the same as the top. That means omega t is not equal to a constant. Simple.
The camera needs to be moved down.
Oh, yes. Okay. So if this was a constant, that's no time dependence, then this is uniform circular motion. If there is time dependence, then that's non-uniform circular motion. So what's acceleration? Acceleration as a function of time, take the derivative of velocity, right? So that's derivative of velocity. So this is equal to, I can now take, remember your product rule, I can either take a derivative here or take a derivative on the second one. Let me take the derivative of the second one first. So this is r times omega as a function of t times derivative of phi hat with respect to time. There is a time dependence in there, but I'm just suppressing it just so that there's clarity. Plus, there is one more term now. I can take a derivative with omega also, right? So that's r times d omega by dt times phi hat. Oops, what did I do? Yeah, this is okay. Any questions at this stage? Okay, if you allow me to proceed, I again take the derivative with phi hat. This, remember, was cosine, and this was a minus sign and a cosine phi. Again, I will get a chain rule. So I'm jumping a step here, but I can clarify that again if necessary. So there will be r, there is already an omega there. There will be another omega, that is d phi by dt, coming from the derivative of phi. And instead of phi hat, this becomes r hat now. Okay. And this we will keep it as it is. R times, this is the rate at which angle is changing. But already omega was d phi by dt. If you want, this is second derivative of phi with respect to dt squared. Okay. And if you notice, there is centripetal acceleration there. So let me rewrite this as omega squared r times r hat plus r second derivative of phi dt squared times phi hat. Let me draw this so that I only want the physical picture to be clarified. The algebra will come out as it is. So what am I talking about? So if we are talking something is going in a circle, that is the position of the object is this. That's your r hat. That's the direction of your position, and this since this is actually the circle itself, so that's actually vector r also. Its direction. So let's say if its unit magnitude is this, that's your direction r hat. What's your phi hat? That's tangent to this. In very simplistic terms, tangent is phi hat, radial direction is r hat. That's it. Right? Position is given in terms of r hat, the radial direction at any point in the circle. The tangent gives you information about phi hat, but what is that equal to? That is a velocity. Velocity is in that direction. But now we are asking, where is acceleration? If it was uniform circular motion, this is 0, right? This is a constant that's equal to 0, that does not contribute. In that case, the centripetal acceleration is purely inward. So centripetal acceleration is this, if this was uniform circular motion. But if it is not uniform circular motion, that could be a tangential acceleration also, and that could be in this direction. So the dotted lines represent acceleration. This vertical one, which is in the direction of phi hat, that can get contribution only if that is a non-circular motion in here. So this is centripetal acceleration. That is radially inward. which is also this quantity in here, and this piece here, that's your tangential acceleration. Which is the tangential means in the direction of phi hat. So in non-uniform circular motion, in general, there is a tangential acceleration in addition to the radial acceleration. Let me do an example where this really comes out, which is also part of your homework. So that should clarify this piece. All of this should come together, I suppose. Any questions before I do that? Or maybe before I do that example, maybe I should summarize this in one place, so that since so again, that's your circle, that's your vector, that is a direction vector r hat, that's your phi hat. And anytime you have two vectors, that's a good way to analyze a problem. So position r is equal to r times r hat. So we are saying it's circular motion, so this is fixed. So this could have time dependence if you. Velocity in circular motion is omega times r. So, but omega could depend on time times phi hat. So its direction is completely tangential. And its acceleration in circular motion, in general, there could be two pieces. One is inward, minus means it is inward, times r hat, which changes direction. So that's your centripetal acceleration, plus r times second derivative of phi. Later we will have a symbol for this, but as of now, let me just write this as how the phi is as a second derivative of time changing, changing in time. So that's centripetal acceleration, and that's tangential acceleration. That's the summary. Like if you did not get the proof, there was a question as to what if, do we have to remember all this? No. If you can get symbolically and conceptually what this equation means, that's sufficient. So the acceleration is not purely radial if the velocity or the speed was changing with time. So this has to do with the speed, how much angle is changing with time. Okay. Example. Let me take a very close example to what we did or what is there in the homework. A particle or an object or a mass is being swung in a vertical circle. So that's your vertical circle. That's your vertical line. And let's say it is making an angle 30 degrees with the vertical. So that's your 30 degrees. And that's your stone if you want. I think it's a stone or a ball that is being swung in a circle, right? So that's 30 degrees. And you're given that the acceleration of this object is equal to the total acceleration, let us say is minus 15 meters per second square in the I direction, plus 15 meters per second square in the J direction. Right. So even though this is your position vector, that's your something going in a circle, the acceleration is not a position object, right? So that's not a position. So it's having different units. But what does that mean? Where does it sit? That's my reference line, let's say. That's your X and Y axis. That's your I hat, and that's your J hat. And since it is minus 15 plus 15, it will make a 45 degrees angle. And if this was 15 degrees, 45, since it is equal, that means the angle it will make with respect to either of the axes will be 45 degrees. So that's your acceleration vector. Right, that's 45 degrees. Like, how do I know that? Because I first of all take the magnitude of acceleration. That's 15 square plus 15 square. That's 15 square root of 2. So that's 15 times 1.4. So let me 15 times square root of 2. So that's 21.2. Let me say that's 21 meters per second square. What's the angle it makes with it? This angle should not be confused with the angle phi that we have. So let's say this is some angle alpha, right? Which angle should I call it? Theta A. That's the angle associated with the vector A. That's tan inverse of, in the second quadrant, 15 divided by 15. That's 1. That gives you 45 degrees. And just to make it specific, this is clockwise with respect to negative x hat. So that's your vector A. So that should be clear, no doubt about that. But what is the question now is what is the centripetal acceleration? But if I want to do centripetal acceleration, I want to change my directions of this vector with respect to a new set of vectors. What is r hat and phi hat, right? That is how the acceleration can also be written in terms of r hat and phi hat. It's a different direction. So where does that sit in? So let's see. So that's again the circle. So that's your point here. Where is my r hat here? That's my r hat. Right at that instant. Where is my phi hat? That's my phi hat. And I need to write this vector. Where is my A here? A in this reference is somewhere here, right? That was 45 degrees, so that's somewhere here. So this is my radial direction. So that forms an axis, if you notice. That's your axis. And with respect to this axis, if I were to say this is my new unit vectors, that's my first quadrant. That's my second quadrant. That's my third quadrant. And that's my fourth quadrant, right? Imagine this to be all twisted, right? It is upside down. This is your I hat, and that's your new I hat, and that's your new J hat. And with respect to that, that's the third quadrant. And that's my vector A. What's the direction it is making? This was 45 degrees. That was 30. Did I say? That was 15 degrees, right? So that's 15 degrees. That's 45 degrees. What is the angle in between? So 90 minus 45, 45 minus 15. So that's 30 degrees.
Wait, where does that 15 come from?
This is the 15 I gave you. So that is the, where did that 15 come from? Yeah. Where did that 15 come from? Sorry. No, where did that? Because where did that 15 go? Oh, that's in the problem, actually. Yeah. This is, okay, question, right? If you have to look into the problem, the problem says that the position of this in the circular motion is 15 degrees with respect to the vertical. Like that's your particle. So acceleration need not be in this direction. Notice that acceleration could be in any direction. So that's your acceleration. That's your position vector making with the vertical. Right? So that's again repeating. It's given in the problem.
I thought that angle was 30 degrees.
Oh, so because I changed the problem, right? I changed. It's not even 15, right? Or did I say it
you
before?
said before that it was 30 degrees with
Okay,
respect
so
to the vertical.
Let's keep it 30. Okay, fine. Yeah, maybe I meant to say that. Yeah, I forgot I think I wrote this 15 and I got confused. Okay. So this is 30 degrees if I said that clearly. Okay, thank you. So let me change this. Is this still visible? Yeah. So let's do that 30. Okay, no more. There's no other confusion, right? Yeah. So this is 15 is the length x component, y component of that. So that's 45. This is 15. So what is the angle it is making with respect to this radial direction? That's this angle here noted. If this is 45, that's your 45. 45 minus 13, this comes out to be 15. If I had chosen that to be 15, this would come out 30 either way. Right? That's 15 degrees. That's the angle it makes with r hat. Right? And that gives me immediately how to get my A. Vector A will be equal. So this is in the third quadrant, so that's minus r hat and minus phi hat. Magnitude is 21 times in the r hat. This is my new I hat direction, right? That will be your, if you want x, right? So that's cosine 15. I cosine because it's adjacent to the r hat. The other one is 21 sine 15. Just going by this diagram in here. And let me quickly do this. 21 times cosine 15. I crossed the time even today. So that's 20 minus 21.3. Actually, it's a very small number, but it's r hat minus of 21 times sine 15. Like within your 2 sig digits, this would be 5. So it's 5.4 phi hat. What is my centripetal acceleration? That's this. If I want to ever get the centripetal acceleration, that's whatever sits in front of r hat. So I know that omega square or v square over r, right? So v square over r or omega square r, which is the same, is equal to 21.3 as a number, not worrying about the negative sign. That's exactly 21.3 meters per second square. In the problem, they ask you for the velocity, that's v, and r is given to you. R is given to you to be 1 meter. So velocity would be equal to 21.3 times 1.0, and then you take a square root of that. Notice that here it is very sensitive to the third sig digit, so one has to be careful whether we keep that or not. In principle, it should, two sig digits should be sufficient. So it just says that the tangential acceleration is really small. Square root. Sorry. So it's 4.6 meters per second. Okay, I'm again short of time, but hopefully this helped. I had a hurry in the end. And probably I confused with that angle also, which hopefully was not too much of a confusion. Okay, I'll stop here. Yeah, and I'll try to clarify this a little bit more in the homework solution. Hopefully that helps. Yeah.
Okay, thank you.
Bye. Any questions? Shall I stop the recording?